Now we have seen how a CPU would execute a program. Now this program was written in the machine language or the language that the CPU understands. In other words, the machine language has instructions which the CPU has the required circuitry to operate that. You might wonder, now these instructions are not like the instruction that I write in my lab classes. They are not the Python statements that I write. So what happens to this Python statement? I mean, where are they? Now, languages like Python are called high-level languages. The reason is that they are more closer to the language that we speak. If you take a single statement in Python language, that carries a larger meaning. Whereas if you take the machine language, they have a very specific, very limited scope meaning to that instruction. So they are much easier to implement in a CPU because they are very primitive. So you can easily translate them into a circuit like the add operation that we discussed in the first lesson and implement it in hardware. So when you write a program in a high level language, that need to be first translated into the low level language or the machine language that the CPU can understand, and after that the CPU will execute that. To understand this, let's look at an analogy. Now we know that in mathematics we have only 4 basic operations: addition, subtraction, multiplication and division. So they are very simple operations that even a very simplest form of a calculator can do. Those are the operations that you learn in school in grade 2 or grade 3. But when we come to high level problem solving, we can't only work with these things, or it is very difficult to work with these 4 operations. So what we do, we create high level functions like the logarithmic, sine, cos, tan, trigonometric functions, or it could be integration, differentiation, etc. And if we look very carefully, we know that these high level functions that we use in mathematics are also built using those 4 elementary operations: addition, subtraction, multiplication and division. So when you execute a high level function, for example, if you want to calculate the tan value, tangent value, or if you want to calculate the differential of some equation, in fact, inside the operation, you get translate that high level function into the 4 basic operation and then execute that. So likewise, when you click on the run button in your Python IDE after writing your program, there's a process that happens inside the computer. In fact, there's a software that carries out that process to translate the high level program that you write into a machine language program first. So that software which does the translation is called the compiler, or sometimes it's also called the interpreter, depending on whether it translates the entire program at once or whether it translates line by line. If it translates the entire program at once, it's called a compilation. If you translate one line at a time, then it's called interpretation. So once you have the machine language program, now that consists of a set of instructions which can be executed on the processor. Now that set of instruction is very specific to the brand and the model of that processor. For example, you have the same Python program running on a Raspberry Pi computer or on a Intel processor based computer. But when the compiler translates that into the machine language, compiler knows what the process that you are using and it will translate to the machine language of that specific processor. So once the machine language instructions are executed, inside the CPU, they are represented as binary values. We call them as the register transfer logic. If you recall, that's how we implemented in our very first add operation in the lesson 1. Then this register transfer logic is then implemented using basic logic gates as a timing diagram or sequence of activities that happens. So if you look at this back again, we have the Python statements which are very high level English language like statements which get translated into the machine language instructions like load, store, add, store, etc. And then that get translated into the binary bit patterns inside the circuitry. In fact, bit patterns are represented by voltages and currents inside the circuitry and then executed as a sequence of activities in the processor. So this is a very long process and a very complicated process. So since the processor can execute millions and millions of instructions per second, we see this process happens very fast. So a single statement that you write in Python, let's say you write a print statement, that might get translated at the machine language level to maybe 50 or 100 different machine language instructions. And that will be executed in the CPU because each machine language instruction need multiple steps to execute, may be executed as 10,000 or 20,000 different operations in the CPU. So the program that you write will get eventually executed as the large number of very small steps inside the CPU. Fortunately, we have computer engineers build systems that can do most of that work automatically. If you look at history of computing, you will see that earlier these were not automated. People had to do this manually. The compilation was done manually. People had to write program in assembly language or machine language instructions. That was a very great challenge for those people, but because they took that challenge and they developed those systems, we have very high level programs that we can work very easily in today's context. Before we conclude this lesson on how computers work, let's summarize some of the topics that we have discussed so far. So we started our discussion by looking at what exactly is a computer. We looked at different types of computers ranging from desktops, notebooks, laptops, etc. that we usually see as conventional computers, as well as computers that sits behind other equipment and control those equipment, or the computers that are invisible to us. And we discussed that many of the day-to-day equipment that we use today are actually controlled by a computer. They sit inside other equipment or embedded in those equipment and help them to operate. Even though they are not visible as computers, we also discussed that they also operate in the same way as conventional computers. They also execute software or run a sequence of instructions to get some useful work done. Then we looked at how different parts of a computer or different modules of a computer are organized. We looked at the basic components like the memory, the input devices, the output devices, and the central processing unit or the CPU is connected through a system bus for sharing information between them. We looked at how data can be transferred between these equipment, these modules, using the system bus. We looked at how an address is used to identify where the data should be sent to or from where the data should be read, and also how we can use the data bus to send or receive data, and how we can use control bus to send commands to those devices to act accordingly. Then we looked at different views of a computer. We looked at how a software programmer would look at a computer and what type of information about the computer that he would need to write software. At the same time, we also looked at how an hardware engineer who would design a computer would look at the problem and what type of information, what type of details that he would require in designing a computer. Then we focused our discussion on the central processing unit, the heart of the computer or the key component that makes a computer to be a computer. We looked at what type of operations that the CPU can perform. We looked at how these elementary operations are constructed using digital circuits. And we also looked at how this elementary operation can be put into a sequence to create a machine language program that the CPU can understand and execute. Then we also went into details to see how CPU executes these instructions. We looked at how the CPU walk through a range of instructions by updating its address and fetching those instructions into the CPU and then executing them one by one. We looked at the instruction cycle and how the instruction cycle is made out of using an instruction fetch cycle and an instruction execute cycle. We also looked at the format, the layout or the structure of a machine language instruction in terms of what is its opcode or the operations code and what are the operands that it needs to perform that action. And finally, we looked at also how these instructions are executed in a CPU. We walk through a small sequence of instructions to see how that happens inside the CPU. And then we looked at the high-level language programs, like those programs that are written in C# or Python language or C++ language, get translated into machine languages instructions and how they are executed as machine language instructions. In summary, we looked at what happens behind the screen when you click on the run button.